Yeah, so I guess as was mentioned, I'm calling in from Toronto, where I am a graduate student and I'm being supervised by Martin Van Kerkwyk. And because of the weird structure of University of Toronto, I am associated with several institutes, which are all the same building. Um, but I am excited to talk to you today about my work with pulsars and how I use them to measure clouds. But it's sort of weird to be giving a talk about clouds to astronomers since we've all had the experience of trying to see something and it's thwarted by clouds. They're the worst. Um, and not only do clouds cause a problem for our ability to see the night sky, we also have to deal with the atmosphere. The term for the sort of effect that the atmosphere does on light that causes it to be distorted and twinkle is called seeing. But what happens is that the light from a distant star hits the atmosphere, it hits different electrons, different particles in the atmosphere, and then it scatters along a bunch of different paths. And so instead of having a nice crisp image of your star, you see a bunch of like small distorted images. And what that ends up looking like when just with our eyes, when we can't really resolve all the tiny different images, is that stars twinkle. So this is supposed to be what the night sky looks in Calgary like roughly now, if there was less light pollution. And I've turned the twinkling up pretty strong, but you'll be able to tell that a lot of these are stars, partly by just knowing what the night sky looks like. You know, you have Orion. But you can also notice, well, two very distinct objects in here that don't twinkle. So there's the moon, and here's Jupiter. So it's often a trick people use to say you can identify that something is a planet because planets don't twinkle. And the reason for that is partly, it's called spatial coherence. So you're saying, it's a really fancy way of saying that it's very small. Spatially coherent means that in terms of space, it's all in one space. And the limit for when something is small enough to twinkle and too big to twinkle is roughly around the size scale between stars and planets. Even though obviously stars are a lot larger, they're much farther away. So they appear small in the sky. And a lot of optical effects depend on the thing you're trying to look at being kind of a point source. That's why when you're teaching things to do with strange optical effects, you will use a laser because you get diffraction and refraction and these strange things with lasers, but you don't with a flashlight. So this will be important as I start talking about pulsars as well. But just keep in mind that if something is a point, then you're going to see these weird twinkling effects. If it's a lot larger, it'll blur out the effects and you don't see the twinkling. Now, if you want to avoid all these problems of clouds and atmospheric seeing, one way to do that is to look at different wavelengths of light. If you are an astronomer or someone who is interested in really high energy phenomena and you want to look at gamma rays or such, you have to go outside of the atmosphere. You put a telescope in space because it's just impossible. All of the light is blocked. So this plot is showing how much light is blocked at different wavelengths. And visible light, we do see it, but it has this weird stuff. So what you really want to do is look in the radio, or at least that's what I do. So then you have, oh, this turned out terribly. Okay. These pictures are really squished. That's sad. There are various radio telescopes, so the point is they look like big satellite dishes and they come in many sizes. The ones I've worked on most recently are Chime, which is a weird half pipe kind of shape. It's not like a normal satellite dish. But I've also helped build this array of telescopes at the Algonquin Radio Observatory. And what's kind of cool about radio astronomy is as long as you have a metal rod that's conducting, you can pick up radio waves. Okay, and if you have your metal stick and you're looking at the sky, it'll look quite a bit different than what we see with our eyes. So the most prominent feature that you're going to see pretty much in the visible light is stars. So many stars. You'll see this is the Milky Way, like the plane of our galaxy, where there's quite a lot more stars, so it looks a lot brighter, and you can't really distinguish individual stars because there's so many. And you have the large and small Magellanic Clouds, but there's also these clear areas that are blocked, which is once again our efforts in astronomy being foiled by clouds. But these are clouds not in the sense of like things made of water in our atmosphere, but dust and gas in the galaxy. If instead you're looking in the radio sky, you don't really see point sources anymore. There's no more stars. They're not very bright in the radio, but the regions that are dark in the optical with these big gas clouds are quite bright in radio. It's largely also these diffuse large structures which aren't affected by twinkling at all. So that's interesting. But there are a few objects that we see in the night sky in radio that are point-like. So those are the three main examples of that. And the name for quasars or quasi-stellar objects sort of implies this. They look very similar to stars in the sense that they are just like little points that we see in the sky, and there's not much structure. It takes looking at their light in different wavelengths to actually tell that instead of being a star, they're very far galaxies, far enough away that they appear to be a point. And they have extremely bright jets of emission. We also see pulsating stars or pulsars, which I will go into more detail about. And there's fast radio bursts are sort of the new thing for looking at small point-like objects in the radio in space. But evidence seems to actually increasingly be favoring the idea that fast radio bursts are sort of really weird pulsars. But what I guess a distinguishing factor of them is that they come not from our galaxy, they're coming from distant galaxies. Okay, so if I redo the plot that I showed of these point-like objects in space from instead of just looking at the visible, looking at pulsars, they're pretty dim, so they don't show up in the map I had before, but their positions are very similar to stars in the galaxy. Most of them are going to be in the galactic plane. And you can still kind of pick out the Magellanic and the small Magellanic Clouds. That's the farthest really that we've been able to see pulsars, unless fast radio bursts are also pulsars. So far, we have a little over 4,000 pulsars that have been discovered, which is actually a problem. There's the expectation is that there's something like 50,000 in our galaxy, and people are looking for more. But these efforts are challenging in different ways. But we've still found several of them, and it's enough for the work that I do. So I should make sure at this point that everyone's on the same page of like what pulsars are and why they are interesting to look at and why it's annoying that there are clouds in front of them. So first of all, a pulsar actually is a star, unlike a quasar. It is a type of dead star, which is a neutron star. And it's possible that all neutron stars are pulsars and vice versa. This is more of an observational classification than something that has to physically do with their properties. But to get a pulsar, or really any dead star, you must first start with a living star. And when a star is born, it'll have a core. It's almost entirely made of hydrogen, and it burns that hydrogen in order to avoid gravitational collapse and create light. And over time, it's going to make heavier and heavier elements in that core until finally it gets to iron. And iron is unable to create energy by fusing into a larger element. And at that point, the star is no longer able to support itself under its own weight, and you get a supernova. The time scale for burning, going from like the birth of a star to the death of a star is several million years, but it takes a very short time between when it starts has a core made of mostly iron and a supernova. So during the supernova, those outer layers of the star are thrown off and you just have the core. And that core starts to collapse, and the weight of the star on itself is enough to cause a process called neutronization, in which the protons and electrons inside of your core are smushed into neutrons and neutrinos. A lot of the energy of supernovas are actually released in these neutrinos. And this is where we sort of get the name for a neutron star, the idea that everything that was the star is now just a bunch of neutrons. But there's actually three possibilities for what happens after this core collapse. It can become a black hole, it can become a neutron star, or it can simply become nothing. The whole star explodes and there's nothing left. But I'm sure you can imagine that an object being as close to a black hole as it can possibly be without actually becoming a black hole is going to have some really interesting physics. Oh, and here's our pretty picture of what supernova remnants look like. So you have both the Crab Nebula and the Vela Nebula, both of which contain pulsars or neutron stars. And that's all the layers of the star that get blown off into space. So this is the sort of environment in which you're going to find them, and why you can also imagine clouds might be a problem here. There's some very interesting structure to the gas that's been blown out during the supernova. Okay, so like I was saying, neutron stars are really weird. They have extremely high densities. They're like denser than a nucleus. Something like 10 to the 18 kilograms per meter cubed. So the usual analogy people say is that they're roughly the size, like they're smaller than a city. The diameter of a neutron star is something like 26 kilometers, but they're in a range a little greater than the mass of the sun, up to like 2.4 is, I think, the current record for the most massive neutron star. And that's at a region where we don't really know what is happening with the matter inside of the neutron stars. It might be entirely neutrons. It might be something weirder. But it means they're interesting to study to try to figure out what that is happening there. There's no way that we can make that on Earth. They're also incredibly hot. I mean, the core of a star has to be hot in order to burn elements. And the core remains hot after supernova, but it slowly cools down. It's not producing energy. So when they're born, they're going to be like several million degrees. And as they cool down, they get down to a few 100,000, which is still very hot. And they also have this very, very large magnetic field. And the thing that this magnetic field allows us to see is the pulsar itself. So the magnetic field is going to accelerate particles out of its poles. And as the particles are accelerated, they create light. There's a lot of debate on how this process actually works, but we know that it happens, and that's sufficient for my purposes. But this also means that instead of most stars where you're seeing it from any direction, it doesn't matter, you're only going to be able to see this the pulsar with where the beams are pointed, or jets. So I have a little GIF here showing a pulsar as it rotates, and partly explaining why we'd call it a pulsar. So this neutron star pulsar rotates. We only see it when the beam is pointed towards us, and so it seems part of the time there's no light, and then as it's pointed, we see a pulse. The rotation of these is incredibly fast. This is because they're so small, they're able to rotate very quickly. And so what we consider to be a slow pulsar rotates every few seconds. A faster pulsar will be a few milliseconds. So it's thinking several thousand times per second. In each rotation, we see a pulse. The rotation period, though, when this happens, is extremely, extremely stable. And so we're able to measure the distance between pulses in terms of time down to nanosecond precision. So what we have is these incredibly dense, very weird objects that work like clocks in space, but also like lasers because they're very small. So with nanosecond precision, we can actually measure the movement in these pulsars towards or away from us with distances down to like 30 centimeters. That's how far light travels in a nanosecond. So one thing you can do is if your pulsar is in an orbit, you'll be able to really accurately measure the orbital period of it, because you'll see that the pulses, instead of appearing at this incredibly stable, regular intervals, they're going to start to like bunch up together if the pulsar is moving towards you in its orbit, and then they'll start to arrive farther apart as it moves away. So it kind of has this like slinky effect. So I've made this little graphic. It's extremely exaggerated because I've made a pulsar that orbits with a similar period to its rotation. So we don't have orbits that are really going at several times per second. But what you're supposed to see here is that they're close together and then farther apart. And we can use these really precise measurements of orbits for incredibly dense objects to do tests of general relativity. So yeah, if you have very dense objects orbiting very close together, they're going to emit gravitational waves. And as they do that, they become closer together. They lose like the energy of the orbit, which causes them to spiral in. So the first piece of evidence we actually had for the existence of gravitational waves was from measuring the orbits of pulsars. And this sort of graph is showing these, it's a pulsar, it's actually a double neutron star system, but this one pulsar, as you measure its orbital period, getting smaller and smaller. And the rate that this is happening was consistent with the emission of gravitational waves. So we were able to do tests before we actually were able to measure gravitational waves with things like LIGO. And now pulsars are also leading the way for other measurements of gravitational waves with pulsar timing arrays. So in a pulsar timing array, instead of just measuring one pulsar in its system and seeing its orbital decay, you measure pulsars in all sorts of different directions. And if a gravitational wave comes in, it's going to squish pulsars in one direction and push them in a different direction. And so in this case, when you measure this change of when the pulse arrives compared to when you think it should, it's going to be correlated across the sky. So you'll have, if a pulsar is like close to a different pulsar, they will have similar differences in their times of arrival. Otherwise, if it's something that's just happening with the pulsar itself, you don't expect those things to be correlated. They don't care what another pulsar is doing. And I'm not sure if people here would have seen, there was a big announcement of the International Pulsar Timing Arrays detecting a gravitational wave background in June. And so with these pulsar timing arrays, they're able to measure much like larger amplitude or larger wavelength gravitational waves than you can with things like LIGO, because that's on Earth. It's a much smaller scale. This is a huge several kiloparsec scale array of pulsars to measure with. Okay, so for pulsar timing, people, what you want is like a really nicely defined time of arrival with a really narrow pulse. But in reality, when you're actually looking at a pulsar, this pulse, it doesn't really look like that. Some of them have multiple components. Some, like this pulsar, for example, it has two very narrow ones, but it does still have two. This one is nice, it just has one. But several of them have like multiple components. They can be really broad. And so if you're trying to say, when does this arrive? Is it like at the very peak of this? Is it here at the beginning? Makes it a little harder. And not only does it depend on the specific pulsar you're looking at, it also depends on the wavelength that you're observing at. So the ones here on the left are all the same pulsar, observed at different wavelengths, or in radio astronomy, we tend to use frequencies. So this is a shorter wavelength observation, and this is a longer wavelength observation. And it's a lot broader at the longer wavelengths, but it also can change how many different components it has, which one is brighter. It all makes it very, very complicated. Okay. And one of the things that makes it complicated is interstellar clouds. So unfortunately, even moving to the radio regime, you cannot get away from clouds. So one thing that we observe with seeing clouds, or a property that a cloud would have on seeing your pulses, is that they'll also create a time delay. So every material has an index of refraction, which tells you how quickly light is going to travel in that medium. If it's in the vacuum of space, your index of refraction is 1, it travels at the speed of light. But in a cloud, you're going to have electrons, and they're going to slow the light down. So the light's going to arrive later than it would traveling in the vacuum. This isn't going to be a huge problem, because for pulsars, at least, they're a point source, right? They're all going to be behind the same little piece of cloud. It'll be slowed down the same. But where the problem comes in is that the index of refraction changes depending on the wavelength of light that you're looking at. Shorter wavelengths are going to be slowed down more. They're more able to interact with the electrons. And what happens is called dispersion. So what this looks like when you observe your thing at different wavelengths, instead of being like all arriving at the same time and being a nice bright line, it arrives later at these longer wavelengths. When you measure the dispersion measure, which is telling you basically the curve of how quickly it changes with wavelength, this actually depends on the column density of electrons in the cloud. So you're sort of counting how many electrons are in the cloud, which is useful if what you're wanting to learn is what is the cloud made of. You can at least tell roughly how dense it is. This example actually is from a fast radio burst, which is from outside of our galaxy. So it's highly dispersed because it's going through way more electrons than if it were much closer to us. So another thing that happens when it goes through a cloud, the light scatters through the cloud, all sort of different directions. And so it doesn't look quite as point-like if you have your original image of what the pulsar looks like. After it goes through the cloud, it's going to look larger. And that size also depends on wavelength. And so the short wavelengths are going to be still small, but at longer wavelengths, it's going to be bigger. And we can see this in your pulses, that here is a short wavelength one. It's very narrow. And as you go to longer wavelengths, it becomes a lot wider. So this width is sort of telling you how wide the image actually looks. And again, it makes it more difficult to decide when the pulse actually arrives, especially at these long wavelengths. Like, this is very hard to tell where this one, starts. Okay, but what this scattering results in is the thing that I principally study, and that's scintillation, which is basically pulsars twinkling. This image on the left, I hope it is also your left, this one, shows the brightness of your pulsar. if you integrate over those pulses and observe it for a long period of time, here's like a little over 2 hours, and at different wavelengths, you'll see that there's these bright patches. With the color mapping on this, black is bright. And it sort of flickers in and out, and it changes frequency where these bright patches are. It changes with time. And that is the result of multiple images from all these scattering that are able to interfere with each other because this pulsar is so small. It has spatial coherence. If you were to look at it, try to plot where all the images are formed in the sky, which you can do with a technique called very long baseline interferometry that allows you to measure really, really small angles on the sky. You can see in this image, these red lines. Every one of them is where an image of the pulsar has formed as it's traveled through these clouds in space. And it's actually pretty small distance on the sky, but each of those images are going to interfere with each other to form these scintillation patterns. What's also interesting for at least this pulsar is that it's like on a line. You don't necessarily expect that with a cloud, if the cloud is sort of just a blob shape. So an analogy that we often use for explaining why this thing might be so flat or like a line is when you look at light reflecting off of a surface of water. On water, you're going to have a bunch of little ripples, and in each ripple, you might form an image. And because your surface of your water is going to be flat, it's like a sheet, it elongates it in a line. So we're thinking that these images indicate that the things that cause the scattering are much less like a big circular blob and more like a sheet or possibly like a tube. But ultimately, we don't really know actually what it is that causes the scintillation. But we can measure things about them. And so one of the ways we can, or the things that we can measure is looking at the delay. As the light travels longer distances because it's been scattered, you can tell from sort of geometry how much farther your light traveled. It gives you the distance to where the cloud is. And you can measure that. Time converts to distance. But we see, of course, that our scintillation pattern changes. And that's because everything is moving relative to each other. So pulsars can be moving incredibly fast. This is a result of the supernova in which they're formed. They kind of get kicked out sometimes, so they can go super duper fast. Gas in the interstellar medium doesn't travel quite so fast. Earth, of course, travels around in its orbit. We know this value pretty well. We can measure the motion of your pulsar fairly well from these pulsar timing. But there's no real way to measure the motion of gas that's not going towards or away from us. Scintillation is pretty much the only way that you can measure gas moving sideways. So that's pretty cool. And what this looks like for trying to observe it, if we look at our scintillation pattern again, you should see that the length of the bright patches changes. So this particular pulsar is in a binary. And so when it's orbiting in such a way that it's moving very quickly relative to us, the time scale for the scintillas is very small. Or the scintillation, it's very small. When it's not moving so fast, the pattern, it doesn't change very much. And so you can measure that length to tell you how quickly the things are moving relative to each other. And since you likely know the Earth's velocity and the pulsar velocity, you can measure the velocity of the cloud. And lastly, you can tell the size of the cloud, which is basically what's the farthest that light gets scattered by this cloud, by measuring basically the angle that it gets scattered the farthest. And what this indicates, and what's pretty interesting, is that these clouds are small. Where, because astronomy is crazy about what sizes of things are, small here means about an AU or a little bit bigger. So AU being the distance between the Earth and the sun. So it's actually a little unclear what the interstellar medium should look like at that scale, because we cannot see it directly. So we have measurements for what we think the electron density, or what density of cloud should be, sort of on very large scales of the entire galaxy. You see the spiral arms of our galaxy. So that's on 40 kiloparsecs, or 130,000 light years. The longest structure of hydrogen that we see in the interstellar medium is something like 4,000 light years. We can observe pretty well like nebulae, which are going to be a few light years. And again, using a very long baseline, well, actually, I think it's just regular interferometry, but using interferometry to measure smaller angles, we can see protoplanetary disks on the 0.1 or 0.01 light year scale. So this is where gas is in the process of forming stars and planets. So we know from the experience of living on a planet that clearly gas has to be able to collapse into structures that are smaller than an AU, right? The sun exists and it's smaller than an AU. But for most things, it's just angular size of something that's smaller than an AU is not something that we can actually see. And so having these objects in space that are both lasers and clocks allows us to actually see this small structure that we wouldn't otherwise be able to see. Unfortunately, though, it makes trying to find the connection between what these things are that are causing scintillation and structures that we know exist in the interstellar medium pretty complicated. So there's a few cases where we do know exactly what electrons and gas are causing the scintillation. We know that when the distance to these scintillation structures are very, very close to the pulsar, then it's probably the supernova remnant in which pulsars tend to live. That's going to be very close to them, and they have enough weird structure that they could cause this sort of scintillation. Pulsars also cause what's called a bow shock. I mean, anything that's moving quickly through space will cause this. It's sort of the speed of it smashing into the interstellar medium as it moves. So you can also tell if this scintillation structure is very close to the pulsar. It could also be a bow shock. If instead the scintillation structure is very close to us, it's probably related to the solar wind. So particles coming off of the sun. And you can tell this because it'll change with year. If the pulsar is very close to where the sun is in the sky, you're going to see more scintillation. And then lastly, there's only one real case where people have made connections with a structure causing scintillation that's neither very close to the pulsar or close to us, and that's in an H2 region, which is caused by a hot star ionizing the region around it. And so at the edge of this, you get a shell where we might see the source of this scintillation, because it'll happen, or it has the possibility of happening anywhere where the refractive index changes in your gas. So it goes from like having more electrons to less electrons, or vice versa. Basically any weird gas structure. And so something I have personally been working on for several pulsars, they might have scintillation screens that are at a similar distance to what is called the local bubble. So what the local bubble is, it's something 14 million years ago, there were several stars that went supernova in the same region. And as the first one went, it was sort of a nice circular structure growing out, but as you get more and more, it becomes this weirder, lumpier space. So you're like a circle with another circle on top of it. And this yellow feature here, that is our sun. So the sun was not part of any of these supernovas, but it moved its way into where this local bubble is forming. So because of these supernova remnants or successive supernova, you have an area that has like very little gas in the inside of it, but also a sharp sort of edge with higher density gas as it hits the gas surrounding. And that's also these purple things in here are where star formation has been occurring because of the collapse of gas at the surface of this thing. And so the last thing I kind of want to show you is the efforts that people have made from measuring all of these scintillation screens and their distances and trying to connect them with different things in the interstellar medium, including the local bubble. So this is actually 3D. So I'm going to close out of this and show you it in a way where I can move around. Wait a second for it to get bigger. Okay. There's actually very few pulsars who've really carefully measured the distances to their screens. It's of the order of like 10. And so for each of these lines here, we have a black bar, and that's where something is causing scintillation for this pulsar. Some of them have several, most only have one, but you can see on these, here's our weird shape of the local bubble again. And it's a little hard to tell, but many of the scintillation structures are sort of near the edge of this thing or inside of it. So it's very possible that this local bubble is a cause of a lot of the scintillation. But where we are at now in the measurement of these scintillation structures, so we really don't know very much about the actual physical structure of this, because we can measure geometric properties of them, but we can't measure the kinds of things that real interstellar medium scientists measure, like their density and their temperature and like what kind of gas they're made out of. But efforts are ongoing. And ideally, if we can measure these things really well, we can get rid of the effects that they have on pulsar timing arrays, but also learn more about what our galaxy is made of. Okay, so there's a couple of questions in the chat. That's, I guess, the end of my talk. I can take questions now. I'm not sure in which order we want to do this, but thank you for listening.
Thank you so much, Ashley. We will turn to questions, and I'm going to ask one right off the bat. What's the scale of that bubble?
Oh, yeah, so it's pretty big. It's 100 parsecs roughly, which if I can convert that in my head to light, I mean, 300 light years.
300 light years, right?
Yeah.
Amazing, amazing. Thank you so much. Okay, we're going to go to questions. We have one here. I'll bring the microphone. Okay, I'm Pastor. You can't see me, but I'm roaming around the theater now.
Okay.
We have our first question.
Hi, Ashley. Thanks so much for your talk. I really enjoyed it. I actually have two small questions. My first is, I'm wondering if we can get the link to this chart that you have up. Is it linked to like a paper or something like that? Because I'd love to take a look at some time.
Yeah, absolutely. Let's see. I had the link actually on the slide. So it's from the paper would be Ocker et al. 2023, but this is like the link to this particular
Awesome.
slide.
Okay.
Yeah.
I just snapped a pic.
Okay. Yes, I would also highly recommend. Stella Ocker does very good work.
I'll definitely give that a read. And my second question is those little spheres, sort of the aquamarine spheres near the local bubble.
Oh yeah, yes.
The Sirius, is one of those the Sirius BE like Strongen sphere? Is that like, I'm just trying to
Yeah, okay, wait, let me go back to the one I can zoom again. So these yellow ones, those are Stromgen spheres. H
Yellow
region,
ones,
Stromgen,
okay.
yeah. So the really big ones, these are similar to the local bubble in that it's like several supernova. We just don't know the shape of them as well to make them all like weird and lumpy.
Okay, cool. Yeah, I was trying to place the scale and I was like, what I'm looking at here. Thank
Yes,
you.
this is very large. This one is extremely large. Yeah.
Awesome. Thanks.
Great questions. Okay, any other questions in the theater here? Yes.
Hi, Ashley.
Hello.
Just wondering, how do you identify multiple stellar clouds on the same pulsar? Like, how does that appear
Yeah,
to a pulsar with just one cloud away?
right. Okay, I should have put figures in this. What the method by which you do this is a little complicated. But if you take this image and you do a Fourier transform, it separates it in like delay versus velocity of what the structure would be. And in that sort of visualization, you can see discrete structures. Um, I can try to pull something up, but it'll be a bit. Um, I should have.
I'll just point out
made
while
fun.
you're looking
Yeah.
looking that up, Ashley.
Yeah.
On the chart on the right, it says MAS, that's milliarc seconds.
Yes.
So just to give you an idea of the scale or how much of, or how little of the sky that's actually representing.
Yes. That's yeah, roughly a millionth of a degree. That's a good example. Sorry.
It's okay to take time. This is a good.
Yeah, I just have to type some stuff. That's the
You're
problem.
not reading something that was that's 10 years old. This is a work in progress.
Well, yeah, I guess unfortunately the thing I'm going to show you is a few years old. But okay, here's an example of some that have several of these things. So in these plots, wherever you see a parabola, each of those parabolas are oh, there's my dog. Each of those parabolas are a different structure. Actually, I should have pulled up Stella's paper because she shows those. But yeah. Let me zoom in.
Thank you. Good question. Simon, you want to take one from online?
Sure. Yeah, that was a great talk. Thank you so much, Ashley. Taking questions from online, somebody asks, regarding the gravitational waves pulsars emit, are they transverse or longitudinal or both? Does it make a difference?
Oh, let's see. I think all gravitational waves are longitudinal. So when you hear about like black hole mergers, it's emitting gravitational waves in exactly the same way as the neutron stars are. They're just a little bit less massive and less dense. The ones that you're measuring with the pulsar timing array come from, well, they're still sorting that out exactly, but probably come from supermassive black holes and their orbits, or supermassive black hole mergers.
Cool. Next question. Does the pulsar timing array measure the gravitational wave arriving here on Earth, or does it measure the change in the position of the pulsar, which is far away as a gravitational wave passes the pulsar?
The latter. You're measuring, yeah, how the gravitational wave affects the pulsars. Wait, I can pull up the plot again.
Excellent. Any other questions from the theater?
Yeah.
Okay, I've got one. So when I explain pulsars and neutron stars to, I'll say, junior high students, I always describe it as I use the Earth as an example where we have a spin axis and then we have a magnetic pole. That's not on the spin axis.
Mhm.
So it ends up being a bit of a beacon. And is it the same phenomenon we're seeing with the pulsar where you've got a spin, because of course you've got a large body that's compressed, and whatever spin it has as a large star, it's accelerated as it compressed. It's like a figure skater whose arms are extended and then bringing them in. The figure skater spins faster when the star it spins faster. But the phenomena that we're seeing is we're seeing a magnetic pole where the radiation is being emitted that is not on the same axis as the spin axis. Is that correct?
Yes, definitely.
That's so
Yeah.
these kids feel-
No, you're totally right. I guess there's a, oh no, this gift is too slow now. Part of them being so fast though is not just the collapse from their own star. If it's a millisecond pulsar, that's almost certainly because it has a companion that it's stealing gas and angular momentum from. So millisecond pulsars are basically always found in binaries with orbits.
Simon has another question from online.
Somebody asks, what drew you to astronomy?
Oh, interesting. It was sort of a combination of things. I would have the classic, like I got a telescope as a kid and I looked at Mars and Mars was really cool. And then I looked at Saturn and Saturn's even cooler. But then I actually kind of lost it. I got really interested in particle physics, which is part of why I'm so interested with this like gas and space. And I'm just sort of generally interested in the things that we cannot see. And so astronomy was a cool way to be able to study these things. It's like, there's so much that we don't know, and there's so much that's very difficult to know. And you have to combine a lot of science together. But I could also say I did go to RASC meetings when I was in undergrad, and that drew me in more. I started doing wanting to do environmental engineering and switch to engineering physics.
Where was your undergrad?
University of Saskatchewan.
Nice.
Yeah.
We have another question from the theater.
Hi, Ashley. Thank you for the talk. I have a question about, I understand that accreting black holes would also emit radio waves.
Mhm.
Yes. So is it possible that those emissions could interfere with the radio signals that you are looking at from a pulsar and somehow throw you off into the analysis that you are conducting?
Let's see. So it's more the interaction with the electrons and the gas that is causing this interference. But I maybe shouldn't circle back to this, but any radio source that is significant, or if it's small enough, it's going to see the same sort of scintillation phenomena. So we can see scintillation in quasars and fast radio bursts. It's harder with quasars because they don't have the pulsing. They're not on and off. You can't actually measure time delay because they're always on. But a quasar, its emission is totally from being a black hole that's accreting. But yeah, the signals don't really interfere unless you were looking at like if they were at sort of the same position in space, but that's rare. I'm not entirely sure I asked the right question there, but.
Could you expand on that and just explain to the audience what a quasar is?
Right, okay, yeah, sure. So a quasar is a type of galaxy which has a supermassive black hole in its center. And it's able to accrete a lot of gas. There's all this gas spinning around it, and some of the gas will not fall into the black hole. It'll get shot out of its poles. And so we see it as like really bright emission, but it's also really bright emission that's only at the middle of the galaxy. instead of seeing the entire extended galaxy.
So it's still a coherent point.
Yeah.
Simon has a question.
Somebody online asks, presumably the distances to the pulsars are not known precisely. So is there a problem with the cycle count in measuring the phase differences of the gravitational waves as they strike the different pulsars?
Yes. So that's part of why with pulsar timing array, it's actually a very small subset of the pulsars that we know of. There's like, I think 60 or so that are in the pulsar timing array, while there's, close to 4,000 pulsars. And the ways that we measure distances to pulsars are, for the most part, not very precise. One way is with this dispersion measure. Let me go to my dispersion measure slide. This tells you how many electrons are between us and the pulsar, and so you can roughly estimate distance from sort of knowing how much more electron you expect as you go with distance. But that's off by like a factor of 2. The most precise way to measure a pulsar is seeing how it moves in the sky with the motion of the Earth, so parallax, the same way that we measure distances to close stars. Yeah, so there are some that we do know the distance quite well, but there are also many that we really don't. And so they can't be included in the pulsar timing arrays.
So, which radio telescope project underway is the one that's exciting you the most? As far as new construction, we've heard of radio telescopes that are spanning continents. We've heard of radio telescopes that are encompassing the orbit of the moon and things like that. What's on the horizon that's going to make your work easier?
Okay, so the two things that I use, I did actually make a plot for this and I hit it. So this is a map of all the telescopes I've used and some of them simultaneously. So for me, being able to get these really precise pictures of like where the different images are being formed from the scintillation structure is super helpful. So the longer the baseline, the better. Like the farther apart your telescopes, the better that is for me. That I'm excited. Just really people using the technique of its very long baseline interferometry more. And then there's also this method that's called cyclic spectroscopy, which they're starting to develop at Green Bank Telescope, and we might be doing with a telescope I use in BC. But it means that when you look at the pulses, instead of just getting their intensity, you get information about the phase of light as it arrives. So that'll sort of tell you how many like cycles of light have traveled through space. So even like more precise measurements of the delay between images.
Thank you. All right, are there any other questions in the theater? See none. Simon, I think he's got one more online.
Yeah, what's the limiting factor with the current generation of radio telescopes?
Yeah, good question. For pulsars, it can be a couple things. They're not very bright intrinsically, so part of it is sensitivity. I can actually show my image properly of the different telescopes. So one of that is just like how big they are. What?
The images don't look flattened now, they look good.
Yeah, okay, they did want to put it in full screen mode, but this is what it was supposed to look like. So right now the biggest telescope is the FAST telescope in China. So-called, it's the 500-meter aperture synthesis telescope. And you can only get a telescope that big by like digging out a mountain. So that's definitely a limiting factor. That's our most sensitive telescope because it's so big. There's that, and then also with pulsars, because they arrive so quickly and they have like such short periods, you need to have really high time resolution, which is something that's like computationally hard to manage. Yeah, so sensitivity and like computation times.
Right, I think that exhausts the questions from the crowd. Thank you again, Ashley, that was amazing.